Well, welcome to our EC&M Tech Talk, our Tech Talk training room today, right? And we're going to be talking about air conditioning and refrigerating equipment. Specifically, we're going to pull some information out of the NEC Article 440. NEC Article 440 is titled Air Conditioning and Refrigerating Equipment. There's some specifics in there that you need to know. If you think about it, air conditioning and refrigerating equipment, we're talking about the compressor and some fans, so we're talking about electric motors. However, in Article 440, it's going to make some changes for us. So remember, the whole code applies, right? The NEC applies to everything in Chapter 4, and in Article 440 is in Chapter 4, Equipment for General Use then. So let's see what we can pull out. Here's what we're going to do. We're going to divide it up into 6 different sections. We're going to take a look and see what Article 440 specifically applies to and what it's about. We're going to talk specifically about electrical installation of the hermetic refrigeration compressor because that's by far and away the most common out there. We're going to walk through a typical installation. We're going to do it up here on the screen, actually. We're going to use a PowerPoint presentation to get through this rather than try and bring in condenser units and rooftop units and all that into our training environment. But anyway, we're going to walk through a typical installation, show you how to come up with all the numbers that you need to know. And then we're going to talk about, well, what if your installation is not typical? What do we do? Well, there's some guidance and certainly plenty of that in Article 440. We'll talk about that. Specifically, we're also going to talk about room air conditioners because they're a little bit different animal, a contained unit, right? And then we also want to mention the disconnecting means and some other important items that are brought out in the article because the code does apply, as I say, to all of Article 440. So let's get started. And as I mentioned, it could be a unit that's in a residential application, commercial applications, industrial applications. On the nameplate, it gives us information on the refrigeration portion up here as well, but we're not going to concern ourselves with that portion, are we? We're going to concern ourselves only with the electrical portion. Now, some of your refrigeration equipment may look like something down below on the bottom left. And if you think about it, whoops. And if you think about it, those are motors. What is it? 1, 2, 3, 4. It looks like motors lined up. They are compressors. Look on the nameplate. All right. We're going to talk about more about this later. But we're going to find out the information that we need to know from the nameplate on both the smaller residential type units and these larger industrial units as well. Over on the right-hand side is what we're really talking about. Here's someone servicing a condenser unit, refrigeration unit, air conditioner, in other words. Look at that black thing, okay, right there in the middle of the screen in the top. And that is our hermetic refrigeration compressor. And that's a little bit different animal than a typical motor. So we're going to talk about that compressor and see how we size the conductors to it, the overcurrent protection, and we'll talk about the overload protection on it as well. First of all, there's a definition in Article 100 for the hermetic refrigeration motor compressor. And it's a little bit different. You don't see any shaft coming out of it. There are no shaft seals. The motor and compressor itself are actually inside of the refrigerant, all sealed inside of that one big black unit. We do have a capacitor down here. Sometimes it takes that extra kick, doesn't it, to get that motor started. So typically you'll see some type of starting capacitor associated with these refrigerant compressors. And very common problem to have is I can't get my compressor to start. Oh my goodness, my air conditioner's bad. No, it's not. Check your capacitor. If the capacitor's bad, you can't get that refrigerant compressor to turn over for you. We need some way to terminate our incoming power, don't we, to that compressor on the inside, to that motor. And so we have some means to do that. What's critical for us is to properly size those conductors and protect them properly. What's required to be on the nameplate? What's called the marking requirements. And that's found in Article 440, in 440.4, I believe it is. But anyway, Yeah, it says that right at the top of the screen, 440.4. So anyway, it must have the manufacturer's, either their name or logo. Most of them probably have the name and the logo on them, don't they? It has the phase and the voltage, single phase or three phase. The voltage, mostly we're going to see what? Maybe some 120, 115, 120, or some 208/230. Remember, and 208 can be single phase. If I just take two legs off of that Y connected transformer, I get single phase 208 then going to my equipment. So voltage, frequency, of course we're going to be dealing with 60 hertz is what we're going to see on our nameplates. And then something called the rated load current, or the RLA, rated load amps, is going to be on the nameplate. In most cases, we'll talk about the variances from that. But what that RLA is, they say the manufacturer comes up with this, right? Certainly. And they say, look, if this compressor is operating at its design voltage, its design frequency, and so on and so forth, and the right amount of refrigerant available to it and so on, then it's going to draw so many amps to produce its rated output, whatever that output is. So that's that rated load amp. So we don't find numbers on compressors like FLC, full load current usually, or something like that. Another item that we're going to see on the nameplate is the locked rotor current, the LRA. Locked rotor current refers to what happens if I can reach in there and grab that compressor and motor and stop it from turning, how much current would it draw when it stalls out like that? And that's the locked rotor amperage. So we can expect that to be higher, certainly, than the RLA. And then what we're going to find is that these hermetic compressors, they have some type of internal thermal protection. And so it's either going to say thermally protected, meaning that the thermal protection is physically located inside the hermetic compressor, or it's a thermally protected system, meaning that the control system, whatever it is that's supplying this compressor, provides the overload protection for the compressor. So that's what's required on the nameplate. Now, 440.6 talks to us about the ampacity and the ratings. And so right away it says, hey, we go back to 310, don't we? Table 310.16. We're going to take a little look at that. So we just say, oh, well, that's easy. We must get the running load amps and take that, or 125% of it, and go to 310.16, and that's the size of our conductors. And no, it doesn't work that way on these hermetic compressors. 440.6 A and B apply, it says. Here's what it should be 440.6 A for hermetic compressors. Use the rated load current on a nameplate for sizing the disconnects, conductors, short circuit, and ground fault protection. Okay, it says for sizing the disconnects. All right, we're going to do that. Conductors, it might give us some more information that can help us out. And for short circuit and ground fault protection. Doesn't say anything about overload protection. Multi-motor equipment is what we have in most cases. That is, and it says use the full load current on the nameplate. We're going to talk about that. That is, for instance, in the condenser units, that we have sitting outside of a dwelling unit or a commercial building or wherever it is. We have the hermetic compressor on the inside. We also have a fan that usually blows air out the top of that condenser unit. And what it's doing is rejecting that heat that's been brought in from the building. And then the compressor takes that low pressure vapor, compresses it, sends it up to the condensing unit. Fan blows air across there, and it rejects that heat that's been collected out into the surrounding environment. Then that refrigerant goes on down and cools our building again, just a complete cycle. Well, that's all part of that refrigeration cycle that we won't get into in this presentation. But anyway, let's take a look at a typical residential application. So let's see what we've got. We've got a condensing unit. This is the condensing unit. That's that big unit. It's mounted on a pad. Probably bought the pad when I bought the air conditioning unit, right? And I sit that on the pad. Over here, I've got a disconnect. It's going to disconnect the power to that condensing unit. Inside of the condensing unit, I've got two motors. I've got my hermetic compressor, probably down on the bottom, and up near the top up here, I have another fan, that condenser fan, that's blowing that air out of the unit and removing the heat from the building then. And so let's take a look at the nameplate on a unit like that. Over on the right-hand side, we see the nameplate. There's a bunch of information up here that we don't need to really pay attention to. It's all on the refrigerant. Well, if we were a HVAC technician, that would all be really important to us. But we're going to look at just the electrical information from down here on below. And some pretty important info. The electrical rating for the compressor. If you'll notice, for the compressor, it says a single phase, that has to be there. The rated load amps, remember we get to define that, says it happens to be 15.4. And then the locked rotor amps is 84. Now, separate from that compressor is the fan unit up at the top, right? So over on the right-hand side, it says I have a single phase fan. Full load amps on it is only 1.1 amps. And it is a 1/5 horsepower motor, 1.1 amps. All right, that's all some good information. Now, let's see. I'm going to install this air conditioning unit, so I need to run some branch circuit conductors from my panel board. I've got to install a breaker in that panel board. It's got to be the right size breaker, type breaker, and all of that. And then it's got to supply this disconnect switch. This disconnect, in most cases, is just a switch. That's all it is. It could be fused, but typically anymore it's just a switch. And we'll take a look at a little picture of that anyway. And so that's my branch circuit, right? All the way down from the circuit breaker through the conductors to the disconnect, and of course into where it supplies my two motors on the inside of the condensing unit. So rather than go to table 31016 and take that RLA and the FLA from the fan motor, look what it tells us on the nameplate. And it's always going to tell us this. Either it's going to use the term minimum circuit ampacity, RLA, or branch circuit, short circuit protection, whatever. We'll take a look at all of that. It tells me right down here, very important, it says my minimum circuit ampacity is 20.4 amps. That means that the branch circuit conductors that are supplying this condensing unit must be able to carry 20.4 amps. The manufacturer tells us that. And then it says that the max fuse or circuit breaker has to be 35 amps. That's the maximum size. And HRCR, heating and air conditioning and refrigeration, per the NEC type breaker. Breakers meet that requirements now with our modern breakers. Not an issue that I'm aware of. You'll certainly see that marked on breakers as well, HACR. Now, let's see here. So let's see, if we go to what it's telling me is my conductors have to be able to carry 20.4 amps, and I'm going to put a 35 amp breaker on this for my branch circuit. Let's take a look then. You may have already started to panic a little bit because you're saying, Randy, I can get by with a pretty small conductor for 20.4 amps. Let's take a look at 31016. So this is just a very small portion, obviously, of table 310.16, probably the most popular table in the code book, right? It's on the ampacities of our conductors. And if we come down now, we've got two columns. We can either use the 60°C column or the 75°C column in order to size the wires for this branch circuit from the panel board to the utilization equipment. Which one am I going to use? Well, let's see. If it's marked, 60, my terminals are marked 60, 75°C. If they're marked 75, I can use a 75°C column. Less than 100 amps or 100 amps or less, and smaller than 1 gauge and all that, then I'm going to use the 60°C column, except I always follow manufacturer's instructions. Most modern air conditioning equipment, it's your responsibility to figure out which column you're going to use. A lot of our modern units use 75°C terminals. So I might be able to use 75°C wire. If not, I'm going to use 60°C wire. I also have a disconnect switch in there. What are those terminals rated for? So Anyway, that's your job to figure that out, right? Figure out the ratings of those terminals. If we look down here and we'll select one. If I look down here, now I needed to be able to carry 20.4 amps, right? Let's see if I can write that. 20.4, or let's be safe, we could call it 21 amps. I know in calculation, you know, less than 0.5, you can drop that. But anyway, let's say I want to be able to carry 21 amps, not 20 because it's 20.4. So I want to carry 21 amps. Well, number 12 wire is real close in the 60 degree C column. In fact, it's fine in the 75 degree C column. Its ampacity is 25 amps. Now that's based upon its, we'd have to also base this upon its conditions of use, right? No more than 3 current carrying conductors, which I wouldn't have in a raceway in this application. And the big item I'd have to look at is ambient temperature. This is the type of insulation, you know, I'm outdoors, so I better use some type of insulation that is suitable for a wet environment. Now, so perhaps I'm going to choose some of this THWN. And I've looked at the information that comes with my air conditioning unit, and it tells me that my terminals are rated for 75 degrees C. And I've looked at the disconnect I'm going to place in there, and that listed switch tells me that it's rated for 75 degrees C on the terminals. So I decide to use some number 12 AWG THWN conductor to run in this branch circuit. Wonderful. And if we go back to 240, right? Remember 240.4? 240.4 says that I put a circuit breaker, a maximum size circuit breaker, on a given AWG wire. Right? And so, for instance, on number 14 wire, I use a 15 amp breaker. On number 12 wire, I use a 20 amp breaker. On number 10 wire, I use a 30 amp breaker. So wait a minute. I'm going to take some number 12 wire and put a 35 amp breaker, is what that nameplate told me on it. Let's take a look and see if we can figure out what's going on. 240.4 talks about conductors. The conductors are protected by the overcurrent protector device in my panel board for short circuit and ground fault. Remember, we saw that earlier back in 440.4. So short circuit and ground fault. There are 3 conditions that can cause overcurrent. Go back and look in Article 100 in the definitions. I can have a short circuit. So if I were to go inside of that, where I terminate that hermetic compressor, and for some stupid reason, unsafe and all of that, I took the black and the red wire and I touched them together, okay, while they're energized. I have a short circuit, don't I? Minimum resistance, maximum current flow. So the upstream breaker back in my panel board is going to trip as quickly as it can. We're going to say it's going to trip instantaneously because of that large amount of current that flows. Instantaneously, look that definition up as well. It just simply means no intentional time delay. So it's very quick, I'm sure in a matter of milliseconds on a molded case breaker, depending on what you're using. But anyway, it'll be extremely fast, and that short circuit will trip the breaker on, you know, in that short circuit condition. Now, very similar is a ground fault. If I were to take and just disconnect that black energized wire for some stupid unsafe reason again, while it's energized, and take it in somewhere in that condenser unit, touch it to the frame of that condenser unit, bam, I'm going to get large amount of current flow because the frame of that condenser unit is all connected back to my, through my equipment grounding conductor, right, and back to my neutral back at the main panel board. So I get maximum current flow most likely once again, and immediately, instantaneously, that breaker is going to trip. So it's going to protect me. That breaker protects me for short circuit and ground fault conditions. It does not protect me for overload. So if all the way up to the terminals or inside of the motor in that hermetic compressor, or the fan unit for that matter, if for any reason I have a short circuit or a ground fault, I'm protected by that upstream breaker. Even if it's a 35 amp breaker in this case. That 35 amp breaker under short circuit or ground fault, it's going to trip instantaneously, no matter the size wire that's supplying my branch circuit. So that takes care of 2 of my 3 areas for overcurrent protection. Back in Article 100, definition for overcurrent, the third type of overcurrent protection or condition that I can have is an overload, where my motor starts to draw just too much current for whatever reason. It starts to draw too much current, more than what it's rated for, and it'll probably carry that for a period of time. But after some short period of time, that motor's going to go ahead and trip on overload condition. So if I have, in this case, we said what was our LA on this motor? We said it was 15.4 amps. So at maybe at 15.5, 16, 16.5, whatever it is it's set for, some percentage over that 15.4 that the manufacturer has decided that overload device after a certain period of time will open up and de-energize my motor for me. So the overload protection is internal to the motor. The short circuit and ground fault is provided by the branch circuit. That's why we can use that 35 amp breaker in this case to protect that hermetic compressor. Because, once again, short circuit or ground fault, the breaker trips instantaneously. Overload condition, the motor is protected. Same type of thing, right? You got on your dishwasher. You drop a fork down there or whatever, and it binds up. You get the fork, you release the rotor, whatever you have to do, and then there's a little thermal reset button in it. So these thermal resets inside of those hermetic compressors, they'll reset themselves automatically. Now, 240.4 then tells me on that number 12 wire that we're going to use, I have to have a, 20 amp circuit breaker. But I'm going to put a 35 amp on it. How can I get away with that? Because in 240.4, it says, yeah, you always have to put, on that number 12 wire, you can't use anything bigger than a 20 amp circuit breaker. All right? However, unless it says 240.4A through H apply. Well, if we take a look, the answer is found in 240.4G. So 240.4, once again, overcurrent protection of conductors. And what 240.4G says, look, you also have to provide some overcurrent protection for different types of equipment. And the very first one it lists in the table, 240.4G, is for air conditioning and refrigeration equipment. Okay? For those circuit conductors, it refers you to Article 440, well, parts 3, 4, and 6. Okay? And so we're going to go right to the nameplate is what it's going to tell us. And that's what we're going to use. So really, my overcurrent protection has gotten pretty easy, right, for this hermetic compressor. I just look on the nameplate. I select my size wire based on that ampacity it gives me. I select my size circuit breaker based on that information it gives me. And off I go, okay? So let's take a look at what we've got so far. Here's a one-line diagram. Maybe it'll help you out too. This is an example. We have a 35 amp circuit breaker. So this would be a molded case circuit breaker. And we're using some number 12 AWG, copper. I put 50 feet in, whatever it is, okay? Doesn't take into account voltage drop, does it? So I'm taking some number 12 AWG we said we're going to run. And this is my condenser unit down below. This is what's sitting outside on that pad. And I've got two motors in there. I've got my compressor and I've got my condenser fan. It told me that the condenser fan was a 0.2 horsepower motor, 1/5 horsepower, so 0.2. And then it on the compressor, it never gave me the horsepower. It just gave me the RLA, the running load amps. There's some tables that I can use. Go back to Article 430. It's a motor. So back in Article 430, there are tables. Let's see. For one, we've got table 430.251A. Conversion table of single-phase locked rotor currents for selection of disconnecting means and controllers is determined from horsepower and voltage rating. For use only with, gives a reference to Article 430, but then it says 440.12 and 440.41. So I guess that table would apply. There's another table it references as well, actually some more, but if I have the particular one I'm interested in this case is 430.248, full load current in amperes for single phase alternating current motors. So I can go and I can look up for the amount of my RLA, my rated load amps. I can compare that in this table and it'll tell me, well, it's whatever horsepower. In this case, I came up with 3 horsepower. And so anyway, that gives you a little one-line diagram. What I've got, the only thing I haven't really talked about yet is this disconnect very much. And that disconnect, most cases, is just a switch. The purpose of that disconnect, it's right by the condensing unit, as we saw the picture. And it's there for safety. It's so that an HVAC technician, electrician, whoever it is, servicing that unit can turn right around, open up that disconnect switch, and put their padlock and tag on there, and they're locked out while they're working on that equipment. Create an electrically safe work condition, right? So it's there for safety. Now, in some cases, there may be fuses in there, or it may be an actual circuit breaker. Just depends. You've got to take a look at your unit and see what's going on. But anymore, quite often, just a switch in there. Now, what if you don't have the typical installation? You walk up on a rooftop like this and you take a look and, oh man, I got all kinds of units up there. I've got, they're all on the rooftops, right? So we've got rooftop units, but even these larger ones, right, that we see, they are most likely, if they're a rooftop unit, then they're going to have the same setup as that condenser, except it's mounted up on the roof. Might have 2 fans in it or more. It'll have a larger hermetic compressor. It's still got the nameplate on there. Follow the rules on the nameplate. One of the things that you're going to run into on some of the nameplates on some of this larger equipment is something called the branch circuit selection current. And instead of RLA, you may see branch circuit selection current. What is that? Well, it's defined in Article 100. And if you're like me and you go read the definition, you might get more confused than when you first thought about it. Okay? But basically, it says it applies to hermetic refrigerant compressors and ones that have their own protection system. So it's not thermally protected on the inside. Typically, it's protected by an outside system. And that system permits current in excess of whatever the rated load amps would be, usually for a period of time. So really, you might say, well, I'm overloading my compressor. Well, they give the term branch circuit selection current. That's on the nameplate. It quite often may replace that RLA value. Use your branch circuit selection current then to determine the ampacity of conductors. Lots of information in Article 440. If you're going to do this, break out that code book, break out your owner's manual, probably installation manual, whatever you've got for the equipment that you're installing, and start taking a look at this. See what you're really installing, see what sections of the code apply. Lots of information. Let's talk about the disconnect a little bit and some other items. The disconnect is required, 440.11. Once again, for safety reasons, we have to have a disconnect in place. Now, 440.12 gets into how we size the disconnect. Boy, there's a lot of information in 440.12. I chose 440.12b1a because it applies to these hermetic refrigerant compressors, what we're talking about. And here's what it said. It said take your rated load amps plus your fan amperage, and you don't use, remember we had the 1.1 on the nameplate? When we do motors, we don't use that number. We go back to the tables that I mentioned earlier in Article 430, and it will tell me what the full load amps is. And it says that the full load amps is, well, a little closer to 2.9 amps. Now, what's interesting is the 1/5 horsepower motor is not listed in the table. I think they have 1/4, then they jump up to 1/2. So they don't have a 1/5 horsepower. However, elsewhere in this 440, it's going to tell me a little later after 440.12, it gets into, if it's not listed in the table, I can take 6 times, or would take 6 times the full load amps, and it's rated amps in other words, and multiply that number times 6 to give me the fan amperage. Well, anyway, I took 2.9 amps is what I came up with. So I have 15.4 amps is my RLA. I came up with 2.9 on the fan, and that comes up to 18.3 amps. Then it tells me in 440.12 to take 115% of that number, and that's the size of the disconnect that you need. So I go to the supply house and I tell them I need a 21 amp disconnect. Get some funny looks, huh? So what I'm going to do is what? I'm going to have to upsize to whatever my next size is. I can go 30 amp, 60 amp, whatever it is. Here's a picture of what I was talking about, typical switch. It looks like a circuit breaker, so we open up the enclosure cover mounted on the outside behind the condensing unit outside of the residence, whatever, commercial building. We take a look inside, oh, there's a circuit breaker. Must be another branch circuit. No, if you take a look at it, there's no number up here on the handle, no 20 or 35 or anything like that. And then there's a little nameplate over here, a little tab actually, and it says no overcurrent protection provided. This is a switch only. So that's what it is. It's a switch. Looks like a double pole 240 circuit breaker. It's not. It's a double pole 240 volt listed switch. And also a couple other important items to keep in mind. 440.9 for rooftop units, it says we must have a wire type equipment grounded conductor through that conduit. And the reason is that's based, came about in a few editions of the code ago. It was due to a fatality where an HVAC worker on a rooftop, no wire type equipment grounded conductor, only the conduit. The conduit fitting coupling was broke or came loose or whatever, and so there was no fault path from the rooftop unit back to the source, and so that length of conduit that the worker stepped on was energized, and he became a fatality, unfortunately. So the rules in the code changed back then to make sure that we run a wire type grounding conductor along in that rooftop to make sure that we maintain continuity along our equipment grounding conductor. 440.10 talks about our short circuit current rating. All of our equipment, we know this, but certainly our disconnect, any control panels that we have, all have to be rated for the proper amount of short circuit current. They must be able to carry whatever the available fault current is to that equipment. So it has to be marked on equipment or on nameplates. There is an exception for 1 and 2 family dwellings. So what we typically see, that value is not on there, simply because they feel like there's not enough available fault current that the equipment would be a problem. Whereas if we're in a large or commercial application, large commercial industrial type application, office buildings, all of that, we could have a lot more available fault current available. So it's required to be marked on there. The disconnect location must be within sight from, just like everything else, within 50 feet and visible from the equipment that we're operating. So if we put that disconnect on the wall, right behind the condenser unit, we're in good shape. We can't use that circuit breaker that's in the panel board, back in the utility room or garage or somewhere, wherever it is, because we can't see it. It's not within sight from the equipment. Also, keep in mind 110.26a, your working space requirements. So it covers the depth of the working space based on a table from your equipment, from your disconnect in this case, back to what's behind you. There are minimum depth requirements there. And so you're looking at 3 feet, maybe 3 feet 6 inches in some cases. And it also covers the width of your working space, where you've got to have 30 inches, shoulder room as I call it, to get in there and work on that disconnect or that equipment. Typically that's not a problem, certainly outdoors. And the height of the working space. So you've got to have enough room, that's 6.5 feet, so you can get in there and not hit your head. Once again, really not an issue when we're talking about these outdoor and rooftop condenser units. Also remember, that reminds me, on the rooftop units, you're required to have a receptacle within 25 feet and on the same level of that rooftop unit. And in 210.8, it's going to tell you that receptacle on the rooftop obviously has to be GFCI protected as well. Also, that receptacle or the disconnect switch, I don't want to mount it on a panel that I'm going to remove. It's not, I don't put it on the cover of a rooftop unit and I need to pull that cover off and set it over here. That wouldn't make much sense, right? So I'm going to have to mount it on something separate that's not going to be moved around. And then Part 6 covers overload protection. And there's lots of information in Part 6 on overload protection of this equipment. They're hermetically sealed. It's either thermally protected or it's thermally protected by a system, one or the other. So it should not be an issue for us. Once again, follow the information on that nameplate. And then the last thing I want to mention is individual room air conditioners. And that's in Part 7 of Article 440. And it tells us what a room air conditioner is that we're talking about. It's all a self-contained unit, isn't it? It has the hermetic compressor in there, the coils, the condenser coils on the back side, and so on and so forth, and the controls are with it. It's all one contained unit. And we probably mount it typically in a window, maybe in a hole in the wall, whatever. It has to have a disconnect. There's a maximum length on that cord that we're going to use for the disconnect. So we're allowed to use the attachment plug as a disconnect, or separator is what it's called. We can use in that cord as well. So we have some type of isolation protection. Now the maximum length on the cord depends on the voltage. For 115, 120 volt units, it's 10 feet. It's 6 feet for 208 and 230 volt units. And then you have to take a look at the overcurrent protection. And so you'll look on the nameplate once again of the air conditioning unit. But what you have to consider is, so for instance, if I have it can be no more than 80%, in other words, of my branch circuit protective device. So if I have a 20 amp breaker, my room air conditioner can't be rated for over 16 amps, 80% of 20 amps, unless I have other loads on that circuit. So let's say, older home, I have lighting loads on this circuit as well, maybe some other receptacles or whatever. In that case, I'm limited to 50% maximum load of that air conditioner on that circuit. So if I had a 20 amp breaker, my air conditioner would have to be rated for no more than 10 amps and so on. So anyway, that is it for today on air conditioning and refrigerating equipment, Article 440. Lots more information once again. We could spend probably a few days talking about all of this and going through different examples and whatnot. So pay attention to your code book. Pay attention to Article 440 when you're installing this type of equipment, and work safe. We'll see you at the next Tech Talk.